of this module. Assume you had the idea, like is done at EPFL, that SIC 500 CS should be a router. By the way, why would we like to do this? Why don't we want SIC 500 CS to be a bridge? There must be a good reason, otherwise you don't just violate the IP architecture just for the fun of it, or you're a bad programmer if you do that. Yes?
Security?
Security might be a reason, but here probably not, because when you connect from GreenMac to that machine, you still probably need to give your password. Things are encrypted over the line. So it's probably not the reason. Can you imagine what's bad with bridges? Nothing? You love bridges. Yeah. Yes?
Is that bridge not full duplex?
Well, full duplex or not, it depends. I mean, this is now a telephone connection, so it's not Ethernet. And obviously the modem has to work in both directions, like very, very, very old modems were half duplex, but they were in the 70s, now they are now full duplex. Bridge is associated in network managers with something very specific. Bridge equals bad equals broadcast, right? In a local area network, we do broadcast for zillions of things. For example, your Dropbox once in a while tries to find another Dropbox of yours in the local area network by sending a broadcast. So there are lots of, we've seen also the DNS-less service called Bonjour that tries to find a printer, it sends a broadcast. So that's very convenient because it makes it very easy to find devices without any configuration. But it makes sense only if you are truly in a local area environment with very high bit rate and where broadcasts are not an issue. Now, if you're connecting to the EPFL from the Kalahari Desert over a modem over satellite network, you probably don't want all the Bonjour broadcasts to reach you. Right? You're not a printer, so you don't want. Plus, your line is perhaps at fantastic rates like 28 kilobits per second, so the broadcasts have to be avoided. That's the primary reason, I believe. So now that you have done this, it's a router. Since it's a router, assume now a packet comes from this router here, ED0X. So you've connected to some EPFL stuff, and now a packet is going back to you. How will ED0X know how to reach you? Now, what will ED0X do? Well, it's a regular router. It doesn't know anything of the weird things with the modem. So it has a destination address, which is on the same network as self. So one of the two IP principles, I will send directly. Sending directly means I'll do an ARP request to find what is the MAC address of GreenMac. Right? Now GreenMac perhaps does not even have a MAC address. Perhaps it's just a satellite telephone. Perhaps it has one because everything usually has an Ethernet port somewhere. But what will happen? I propose 4 solutions. Which one do you think makes sense? So I think there is it's not ED0X that will reply, right? But SIC 500. So let me correct this. Pen. Okay. So it is this machine. That's the intended question. I should be able to repoll. The question is probably, your poll has probably been lost. You have to put it again. And number 4, it's green Mac, not green mat. So let's see your solution. And the majority vote is the correct one. And this is, in fact, called proxy ARP. So whenever you have that kind of deviation, you need to configure proxy ARP to handle the ARPs. Now, what is proxy ARP? Well, proxy ARP means that one machine responds to ARP request with his own MAC address, or their own MAC address. So here, SIG500CS will respond with its MAC address. So ED0X will send the packet to the MAC address of SIG500CS. Of course, SIG500CS needs to be configured with its own internal routing table. It needs to know that green MAC is on the modem port, which has to be part of the modem connection establishment here. So it needs appropriate configuration, which is typically done specially for modem banks. Right. So this is proxy ARP. It's done at EPFL, for example. If you configure your machine with a network mask equal to 16 bits instead of 24, as it should be, and now your machine sends a packet to an EPFL web server, then what will happen? You will do an ARP, because your machine believes I am on the same subnet as the destination, because EPFL is one big subnet. That's what this mask means. So it will send an ARP to find the MAC address of whatever EPFL machine we talk to. What happens to this ARP request? Well, EPFL routers all do proxy ARP. Whenever they see an ARP for an EPFL address, they respond with their own MAC address. So my machine, if it's configured in this stupid way, will receive from the router the MAC address of the router, except if by accident the destination is truly on my local area network, in which case hopefully the proxy ARP service at the router is configured to do proxy ARP only for the LANs on which this router is not, only for the remote LANs. So if I'm connecting to a remote server inside EPFL, the next hop router will respond to me with his own MAC address. So what will my machine do? It will send to this MAC address, which is the router. Now the router receives a packet. It's a router, it's well configured, it knows where is the final destination, and then it will forward it finally to the correct destination. If we do this, we have to verify the routing table. Is this routing table correct? This is the routing table at SIG500CS. Let's see what you think. Yes, although here it was a bit ambiguous, but obviously you had the same ambiguity as me. So we assume ETH1 is this interface. So this is what is done at EPFL, that typically the modem side of this machine has pooled, in fact, part of the address space that belongs to this subnet and has put it on the other side. Voilà, that's the kind of tricks that are done. Now, if you go to real enterprises, real development, you will see a lot of those dirty tricks being done. Try to avoid them as much as possible, but if you see them, then the best thing to remember, if you see it, detect it's a violation, and if it's a violation, look for the correction to the violation. There must be somewhere else something to fix the problem. Here, if we do this violation, we need to do several things. We need to configure proxy ARP, and we need to configure routing tables at this box. We've seen MTU, path MTU, tunnels, translation. There are some side effects between the two. For example, here. Now I return to the previous topic. My client is on IPv6, my server is on IPv4, and we use NAT64 to go from client to server. What is the value of path MTU at server 4 for the interaction with the client? This is a web server, it uses HTTP. When we use HTTP, in principle, we try to avoid fragmentation, and the way to avoid fragmentation is to detect the path MTU, either actively or statically by configuration. And in TCP, there is a field called MSS. When we open a TCP connection, we declare what's the maximum packet size. So what should it be here? I assume all links are Ethernet, regular Ethernet, or pretend to be Ethernet. Don't be shy, it's not graded. So let's see your solution. The correct solution is the majority vote, 1,480. Why is that? Well, the packets on the blue internet are 1,500 bytes, and here too. So why is it that we reduce by 20? Well, it is because of the header translation. If I generate here a packet of size 1,500 bytes, when I will replace the IPv4 header by an IPv6 header, it's 20 bytes more. So if the packet was already 1,500 bytes, I'm stuck. It won't work. I have to discard the packet. So the NAT64 will have a problem. So the only way to do that is to have a path MTU that is a bit smaller. So we find one of the root causes from these very many different path MTUs that can cause trouble in the internet if you're not careful. There are very often those type of boxes, we will see in a minute other ones, that do something to the packets. So invariably, whenever you do something to a packet, you reduce the path, the MTU size. In practice, in a case like this, it is very likely that the following will happen. In practice with IPv6, many IPv6 protocol stacks do the following. In IPv6, we say there is a minimum packet MTU size, which is 1280. So any IPv6 implementation has to support 1280 packet size, bytes for packet size. Since 1280 is large enough, many software stacks will say, I will not try to discover what's the optimal packet size. The larger, the better in principle. If you're transferring a video file, if you have large packets, you have fewer packets, so it's better for everything. better for the processing in the hosts in particular. But since in IPv6, the leeway is only between 1280 and 1500, so many implementations will say, I'm happy with that, so I will assume that I can have packets of size 1280. Therefore, I will advertise an MSS of 1220. Why did we lose 60 bytes here? This is IPv6 header and TCP header. We might even do a bit less if we support some additional options. So in practice, this is what will be done, and then this is very far away from 1480, therefore there will be no problems. In fact, this values of 1280 for IPv6 has been chosen to be well comfortable with all those kind of issues. So if you start adding or removing bytes to packets in order to avoid fragmentation and path MTU problems, in IPv6 we decide to have a default value which has some margin compared to the physical packet size. At the cost of some inefficiency, we generate packets that are not as big as there could be. Voila, that's the end of this deviation chapter. Any questions? None. Then we move to another chapter called tunnels, which is in fact another form of deviations. Tunnels don't exist in the standard architecture, but they exist a lot in reality. And tunnels, as you know, are a Swiss specialty. We love tunnels in Switzerland. We build the largest tunnels in the world, almost. And tunnel is one of the widespread solutions that come practically automatically as soon as you deploy IPv6. If you deploy IPv6, you'll be forced to put some tunnels. And in fact, when you've used IPv6 in the Internet Engineering Workshop, the IPv6 wireless service that we provide, you've used some tunnels. We tunnel, in fact, over the IPv4 of Internet. What is a tunnel? Formally, it's synonym to encapsulation. Tunnel means whatever happens when you put packets inside packets in the order that is not as expected. In principle, the inside of a packet is a higher layer compared to the outside. You put IP in MAC and TCP in IP and HTTP in TCP. Now, if you put something in the reverse order, it's called a tunnel. For example, you could put an IP packet in UDP or in TCP. You could put a layer 2 packet, PPP, which is a very lightweight header you add on modem lines, for example, on point-to-point lines. You can put that in UDP. You could put an IPv4 packet in IPv4, or an IPv4 in IPv6, or an IPv6 in IPv4, etc. This is always possible, because a packet, after all, is only bits and bytes. Our view of layers is purely dogmatic. It's not based on physical reality. We impose it to make things manageable, but in practice, of course, we can do everything every way we would like. In theory, we never do it, because in theory, we have the 5 layers models of TCP/IP that we should follow. In practice, there are at least 2 important reasons: security and private networks, that are one reason, and IPv6, IPv4 interworking. To start the story of tunnels, let's start with the toy example. Assume Homer has deployed a network, and like practically everybody does, you use private addresses because you don't bother buying address space from a provider, which is fine as long as you're at home. But now Homer has a very successful company, well, probably not Homer, but and has a second site, right? So now I can use 10.1 for this site, 10.2 for this site. Then I want to interconnect them together. How can I do it? I would like to interconnect them and still keep a private network. See, this is my business, and I don't want this network to be open to the outside. How can I do it? I propose here 4 solutions, including one solution that says it's not possible. What do you think? Let's see your solutions. Okay, you're influenced by the topic of the... this is certainly a correct solution. 2 is also possible. You could rent a lease line from whatever provider. What is a lease line? Well, it means a physical connection that's only for you. In fact, it's not physical, it's switched inside probably a tunnel. But to you, you don't see that. So it's. You could also use modems by having a telephone at A call B, and then use that to connect the 2 routers. But it's a bit old-fashioned. You do that really in extreme cases when nothing else works. So certainly the solution of choice would be there. Wonderful. Homer uses an IP over IP tunnel. Right. So what do we need to do when we have an IP over IP tunnel? Well, we assume we receive an IP service from a provider, here Simpscom, and gives to A and B IP addresses that are in the pool of addresses that are owned by this provider, 111.222.2. Then what do we need? What does the private network need to do? Well, we need typically to configure the tunnel, which is viewed by the systems we use as a virtual interface. So this A has a physical interface, which is the connection to Swisscom or to Simpscom, which has an address, 1111. Now, you add on this interface another interface, which is now a logical interface, which will appear on your operating system as another one. So you will have ETH0, ETH1, ETH2 if you're in a Unix type of environment. You will need to do something similar at B. And now you will need to configure the routing tables at A and B. If you have only 2 routers, you probably do it manually. If you have more than 2, you use RIP or something similar. And then you will have a network where A and B communicate over the internet, but inside a tunnel. Right? Packets from S to X will be carried inside IP packets across the red network. Right? For example, if S sends a UDP packet to X, what are the IP destination address and protocol at this observation point here? Let's look at your solutions. Well, at least part of it is right. The destination address is this one, that's correct. But we said we do IP in IP. So the protocol type I will see is IP. Right? So what I will see, so the correct answer is none of the above, but I admit it was a bit tricky. The correct solution is the protocol type will be IP. We have an IP packet in an IP packet. Right? So we have, this is why it seems a bit weird. I mean, why do I have in all the list of possible protocol types that I can see in an IP header? I can see IP itself, IPv4, which is 04, or IPv6, which is 4.1. In this case, it would be IPv4. Right? Of course, inside the IP packet, there will be an IP packet, and in the internal IP packet will have protocol type UDP 17. So Homer's solution, IP in, yes?
The IP address of the inside of the inner packet destination address is 10.1.1.1.
Correct. It will be this one, right? So in fact, what we have done is we have replaced the internet by an illusion of a local area network. We use layer 3 in the same way that layer 3 normally uses layer 2. Right? Which is not surprising if you think about it. The MAC layer is itself a networking layer. I should not say that because I'm sure you will oppose to me in the tests, everything. It's not a layer 3, but if we, now that you have had enough exposure to what TCP/IP really is, we can understand that those numbering and numbers, etc., are a bit artificial. The only thing that's important is how it is organized, how it is intended to be organized. So it is intended to be organized that IP views the world as local area networks that it interconnects. But if the thing that it interconnects is not really a local area network, but an IP tunnel, then it will work the same way, right? In practice, we don't see very much for networks like Homer. We don't see IP in IP for bad reasons, but important reasons. The bad reason is that most company firewalls kill IP in IP packets because they suspect something weird. But they accept UDP packets. So some people believe we do security with things like this, but of course, as soon as you put a rule, people find a way to go around the rule. So because of that, essentially, very often we put the IP packet in a UDP packet inside an IP packet. So the cost is 8 bytes of UDP packet. It's even worse than that. Usually, we also add a PPP header, a layer 2 header, so that if we have the complete thing, we will see the red packet, the packet that the operator sees is an IP packet with destination, an IP address that is this one. Then it's a UDP packet, so all the filtering routers are happy, they see UDP packets, right? And then there is, usually people want to really emulate what we would have if we would have a local area network. The main function of a local area network here is a stupid one, is to say which protocol type you are carrying. And which protocol type in practice is only one of two, IPv4 or IPv6. So here it would be IPv4, and then you have all that stuff here, which is the blue packet. Now when the A box receives this, the destination of the packet is the A box. This is a tunnel endpoint, so this is a specific router that has a process called the tunnel. So the tunnel receives this, and it sees, oh, it is for me. It is the tunnel that I have correctly configured. I read which is the protocol type. I use this protocol type to do what? What will this guy need to do with the blue packet? You will need to put it on the blue environment, but you will put it on Ethernet. So if you support more than one, if the only thing that's always supported is IPv4, it knows it's an IPv4 packet, so it puts ether type equal IPv4. But if you want to be flexible and support IPv6 as much as IPv4, then you would look at the protocol type to know what to do, and therefore put it on Ethernet with the correct protocol type. So this is what is done in practice. In practice, we even do more, because usually if you do this, you also want to encrypt the data that you sent over the internet. So the complete story is that one. You will typically, at B and A, have a security association between A and B, which means they share secret keys, which can be derived from a public key infrastructure, which allows to use something called IPsec. IPsec is a very simple mechanism of security that uses symmetric cryptography to encrypt all the payload. So everything that is after the IPsec header is marked as XX. That means it's encrypted. And then there is an IPsec trailer to be able to correctly know when it finishes, because if it's encrypted, you don't know when it finishes. So this guy here will receive the blue packet, will do all the things we said before. He will add the IP destination address, the public destination address, UDP and PPP. PPP, in my opinion, could be avoided, but here it is done. And now the protocol type is 50, which means what? It means IPsec, right? And so there will be, it means it is an encrypted stuff. Now there is the IPsec header, which will itself give the mechanisms to know which encryption system is used, and also, and that's it. So that whoever reads the traffic here will be able to see, well, there is traffic from A to B, and it uses IPsec, but you will not see anything of the, in fact, of the packet here. So that is very similar to what you would have if you would have a list line on which you have put your own so-called one-sec security. At least on a list line, typically you encrypt all the data. So this is what you get, but you don't have a list line, you just have your regular internet access. Right. So this is what is used in what is called VPN. Now, when you see VPN, you add 4 or 5 letter acronyms. So L2TP means this layer 2 header that is added, and IPsec, that is the form of encryption that is used. There are other forms of encryptions. There is TLS, for example, typically used with OpenSSL. OpenVPN is a variant of this that uses slightly different encryption mechanisms, but is essentially the same. So this is typically what is used in what is called VPNs. For example, at EPFL, you can access the EPFL network also via VPN. I'm showing here an example where if you go to the wireless EPFL network called EPFL Public, and you want to access the regular EPFL network, one method is to go via a VPN server. So if I do this on my machine A, and I look at the configuration that I obtain, here is, for example, what I could read. So it's similar to Homer's case, except on the left, there is only me. There's not an entire network. And then I access via a public network, which is here the wireless LAN. And then I want to go to my private network here. So what I will see is this is Windows terminology. In Unix, we would have ETH0, ETH2, etc. In Windows, it's a bit more verbose. So it is showing here 2 interfaces. One interface, which is 192.168.133, for example, which is the physical interface of the network on which I am. And then it shows a second interface, which is the virtual interface, which is the one we have when we remove the data from the tunnel. The 2 interfaces exist. And in fact, if this is a wireless LAN on which there is a printer, for example, I might want to send data to the printer, non-encrypted. It's printed in a corridor anyhow, so if it's confidential, don't do it. So I might need to use both. Now I see that the IP address that I have on this virtual interface is an EPFL address, right, of the 83 pool here. Once I have established this, of course there's encryption with TPFL, typically L2TP and IPsec. If B now, I connect to B, which is a web server or my file server at TPFL. When B sends a packet back to A, how does it find its way to the final destination? I propose, do we need something special? I propose two things special or nothing special. What do you think? Let's see what you think. We need to do something. We need to do proxy ARP, because when B sends a packet to A, the destination address is in fact this one, hopefully. When A speaks to B over the tunnel interface, it pretends to be inside the EPFL network, and it will use this as source address. So when B will receive a packet from A, it will receive a source address, not the 192.168.133, but that one. So B will respond to that address. Right? In fact, the other address is a private address that probably you cannot communicate with from B. So it will send a packet to this, but the packet will be forwarded by R to the local area network where the VPN router resides. Now we're exactly in the same situation as before with the modem. In fact, the VPN is the modern way, alternative to modem. So we will have exactly the same problem. R will do an ARP request for the IP address of A, the virtual IP address of A. And if the VPN router doesn't do ARP proxy, we'll have a problem. Or at least we have a problem. One solution is that the VPN router does proxy ARP for A, so the VPN router will not only need to manage all the tunnels, but also do proxy ARP for all the addresses that are given over the tunnels. Voila, that is all we will say about VPN tunnels. I don't discuss the encryption, how the keys are distributed, all that stuff, which is fascinating, but is a topic of the course on security. Here we're interested in networking and how we put things together. As you can imagine, we do tunnels also for IPv6 and IPv4. So again, the same slide, but I think it's important. IPv6 to IPv4 is a nightmare if you don't put a little of order. So now we're discussing like-to-like access. We're finished discussing with interworking. Interworking is either application layer gateway. We will discover perhaps next week that there are also transport level gateway. But the main thing is application layer gateway, or NAT64, true translation. Now we're interested in another type of problem, which I call like-to-like access. It's an old terminology that you don't find very much in RFCs and today's document, but I think it says very well what it means. Like-to-like means I have two things that speak the same protocol, and they have to communicate together, but over a cloud that is not the same. For example, IPv6 to IPv6 over IPv4 internet. This is what is called the early adopter problem. Assume you run IPv6, which is practically what happens today. If you run IPv6 today, you're probably in an academic network or in this TPFL, or a place like this where we find it interesting to do IPv6 because it's futuristic, but you don't buy pizza with that, right? You just show and experiment with it. But hopefully there are others like you, other geeks in the world like us, are also happy to see the IPv6 logo when you go to a web server. But the world between us is not always IPv4. For example, when you are on the wireless network of EPFL, as you know, we have only IPv4. Some providers in Switzerland provide also only IPv4. In fact, most providers on cellular networks provide only IPv4. So if we have IPv6, we're probably in that situation. So the question is, how could I speak to another IPv6 machines given the end-to-end path is not entirely IPv6? Right. I should add something here, is that there is the concept in the internet, when we talk of IPv6 versus IPv4, that there is a single IPv6 internet. So if you pretend as a provider that you provide an IPv6 service, you have to connect to all the other providers in the world that provide IPv6 with IPv6 connectivity. So we will not have several disconnected islands of IPv6, and the same is expected to be true for IPv4 when IPv6 and IPv4 have exchanged their roles. IPv6 becomes dominant. So we can speak of the IPv6 internet and the IPv4 internet. Later, I don't know when, perhaps one day you will see this, you will have most of the internet is IPv6, and at home you get only IPv6 service, but a few people, they have very robust machines that continue to work and work only with IPv4. That is a problem that might continue to exist, for example, because the telephone in the lift is an IP phone that works with IPv4. The manufacturer of the telephones of the lift doesn't exist anymore. It's all done in boxes that nobody can open, so printers, embedded devices. People are deploying smart grids or Internet of Things where they're deploying everything in IPv4. So when those sensors in the mountains and everything will be deployed, nobody will go there to change the software to make them IPv6. So that will unfortunately happen. Although, of course, if you start something new today, you should at minimum make it bilingual, IPv6, IPv4, right? You should not have to change it. How do we solve those problems? With tunnels, of course. Right. So tunnels means simply, if I am in IPv6, I have an IPv6 packet that I want to carry to some IPv6 guy, then we have essentially a simpler, in principle, a simpler problem than the interworking problem. We have two guys who speak the same language, so it's like you're sending an email to somebody who speaks French, and you write your email in French through a sequence of SMTP servers who don't even know French, but still they will carry your stuff, and at the end we can read the thing. So it's in principle a simpler problem. So what will happen is this packet, which is IP and transport layer, will reach the tunnel at A, and exactly like before when we had Homer over the public internet wanted to interconnect private islands, we will put it inside an IP packet. Now, the IP packet can very well carry an IPv6 packet. Of course, we need a special protocol type for IPv6, but as we know, that exists. At destination, the tunnel will decapsulate the packet, remove the blue header, and has an IPv6 header. Said like this, it is simple. Of course, there are a few things to solve. We need to solve a number of things. Like, if I am like Homer, I have two sites with two routers and one tunnel, it's easy to do. But now, if we do this IPv6 over IPv4, we may have many, many little islands like this, and you may want to communicate to many, many other places. Like, there are many, if you do that from EPFL today, there are many places in the world that run IPv6. So one of the issues is, how do we configure all those tunnels? Does EPFL have to agree with all the campuses in the world that run IPv6 to agree manually on a tunnel? Obviously not. So we want to have something that automatically manages the tunnels. So that is exactly the topic of the solution we'll see. So we need automatic tunnel. We need that the A and B machines will, hopefully without configuration, will automatically build tunnels when it is needed and know how to decapsulate and what to send, where to send the packet. Voilà, that's all we will see for today. How this works in practice and how it can be made